Recording. Okay. So this is 179. A hand is up. Yeah, somebody's hand is up. What's your question?
Someone is saying you should make the fonts bolder.
Bolder. I thought I just did. I kind of remembered late, sure. But I did.
I think you should zoom in on your screen instead.
Yeah, because this is as big as I can manage. Okay, so if you look here, you see iterative 0.544, recursion 0.184, right? This is it, Fibonacci iterative. This is what this console of time is talking about. Okay, so you can see with a smaller number, I think this is even another reason why people bother about performance of code, because not all codes perform, will I say, efficiently or best at all times. I think this is a very good example of that. Some codes perform well, under these situations, but not well under that situation, that kind of thing. So in this case now, we can see with small numbers, the recursive method at least was faster. If I maybe try to do something to make it run again, okay, it's not running again, sure. Okay, it did run again. This one is even, the gap got even more safe. Yeah, so with small numbers, recursion wins hands down. But now if we were to try bigger numbers, 6, and I make this, that day we tried 40, so we might be here a while. I think it took like 20 seconds for it to run. Should I try 30 instead? 30. Right. So you guys can see this, right? Recursion now is 178 ms and iterative is 0.2 ms. So as the number grows, this one becomes less efficient while this becomes more efficient. So some codes are like that, at a small, will I say, with small data, they look like everything is okay. But then if you were to increase the size, increase the sample size, increase the data size, you start getting stuff like this. Like you start seeing, like, say, the inefficiencies of the code. So big O is just a way to sort of classify how well a code is performing, and let's say generalize it, that kind of thing. So it's important to have precise common vocabulary to talk about how our code performs. That was part of the reason why big O was created, and it helps to identify inefficient parts of code. These codes we are writing so far, just, will I say, kind of simple things. It performs one task only. Sometimes a code base would have a lot of functions doing different things. So for some reason, maybe this part is performing well, the other part is not performing so well. So trying to use big O, notation to look at different parts, you can see, okay, maybe this one, the big O, is not that great. Maybe that's why the whole system is not, running as well as I expect it to be, that kind of thing. So another reason why we might want to learn big O is for interviews. Yeah, it's sad, but that's how life is. Because you will be asked, it's good to learn it, because you can be asked, why, what is the big O of this function, that kind of thing. Maybe.
Does that apply to front-end developers?
Yes, it does. Applies to everybody. The point of
But why?
JavaScript is to solve problems. Front-end development is not just about the interface.
UI.
It's not just about the UI. It's things like fetching data. When you fetch data, you have to use it in some way. Sometimes you may need to work on it somehow, maybe change some things, use that data to calculate some things, or that kind of thing. So in fact, without even fetching data, just take that Metro carousel for example. There were functions in there that required you to think. You had a problem to solve. I want to do this. How do I do it with JavaScript? You write functions. The moment you start writing functions, you need to start bothering about big O. So if you are a front-end developer that is not writing functions, fine, it doesn't concern you. But as long as you are a front-end developer that is writing functions, then you need it. So this is DSA. Okay, so let's try something. Let's look at these two codes. The problem these two codes are trying to solve is to sum up all numbers up to n, right? That's simple. So let's call it sum up 1 and sum up 2. Sum up 1, yes, it will take n. And the most straightforward way to write a function to sum up all numbers is to just run a for loop. So you create a variable, let me say I saw this now. Yeah, we create a variable, let's say let sum be equal to 0, and then for I is equal to 1, sorry, for let I equal to 1, because no point starting from 0. Let I equal to 1, I less than or equal to n, because we're getting up to n before we stop the summation. I plus plus, and then you say sum plus equals n, and at the end, or rather after the for loop, you return sum. Right, this is a simple stuff. Console.log, just to show us that it's working. Sum up 1, maybe 5. Okay, Coca. Okay, 25. Oh, n. My bad. I. Okay. 15. So 5 plus 4 is 9, plus 3 12.
There's no Android charger inside the house. Android charger.
Make person mute themselves now. Was that Johnny? Well, that's alright. Okay, so now let's look at another way to write this same code, or rather to write a function that solves this same problem. So function sum up 2, again it will take n, and now it's just going to return n times n minus 1, or is it n plus 1 over 2?
N plus 1 over 2.
Okay, it's n plus 1, okay, thank you. Sum up 2 5. Okay. All right. So if sorry, if you're not aware how this came about, it's just arithmetic progression in maths, AP, sum of, everything in a series, arithmetic progression series in AP. That's the formula. So now, looking at these two, if we tried that same, console.time and time ends, should we, let's just do it. So console.time, what do we call this? We call this 1. Console.time end 1. Okay. So if we look here, there doesn't seem to be that much difference at this point. Let me try changing this to 10 and we'll see what the difference will be. Okay, this became 3 point something. This one didn't change so much. It was 0.2 something before, right? Not much change. Maybe 20. It's just hovering around the same place, while this one is changing and changing. So let's try something a lot bigger. This is 1, 1, 2, 3, 1, 2, 3, 1, 2, 3. That's a billion, right? Okay, still running. Okay, so back here, this second one still remains, under 1 millisecond. This one took 6 seconds. Okay, so if we try to analyze what's going on here, we can sort of keep track or try to understand why this one took so long by counting operations. So this is an operation. In fact, it's 2 operations. I think there's a pictorial something on that. I'm pretty sure I saw that in somewhere. Aha. So, okay, over here. Yeah, this is a comparison, right? Is I less than or equal to n? Comparison. This one is an addition and an assignment. In here we have addition and assignment again. But the thing you have to note about these operations is that they increase along with n. So when n is 5, there are 5 comparisons here, 5 additions and assignments, 5 additions and assignments, this place. When n is 1 billion, there is a billion additions and assignments, a billion comparisons, a billion additions and assignments. You get the point. As the number you are working with, I beg. if you open mic to talk, when you finish, you close it back now.
Oh, sorry.
Yeah. As n is increasing, or rather as the size of the data you are working with increases, the amount of operations you are doing increases along with it. So if we were to count this now, this is n plus n plus n plus n. I think it's about 5n, right? 1 2 3 4 5. Yeah, that's 5n. So that means if there are 5 things, you'd have 5 times 5 operations. Well, there's also this one to total. This is an assignment operation. So we can call that maybe like 5n plus 1, that kind of thing. So let me just write it here. But now let's look at this second code. What operations really are happening here? There is 1, there is 2, there is 3. That's it. So 3 operations basically. There's no n anything. Whether this is 5, it's 3 operations. Whether this is 1,000,000, 3 operations. No matter what, 3 operations. Okay? So just looking at this, you can already begin to see differences. So at least at the beginning, there is what is called a function that takes constant time, as in no matter the size of the data you are working with, the operations are constant. Yeah, so that is O of 1. I'll explain later why it's 1 and not, like in this case, we would still call this O of 1 and not O of 3. I'll explain that later. And after that, there is linear time. Linear time is O of n. So as the size of the data you're working with increases, the number of operations would increase along with it. So this is linear time actually. Ignoring that there's a 5 here and there's a 1 here, we would still call this O of n. Again, I'll explain later why it's not O of 5n plus 1. And now there's also what's that thing called? Squared. Is it odd? Quadratic, yeah. Quadratic. So this one mostly occurs with nested loop. Okay, I can't write square here, but I think that you can still understand. This is n squared. Okay, so most times that you see this, it's in something like maybe for maybe okay, let I be equal to 0, I less than maybe 5, I plus plus, and in this loop you have another for loop for let maybe j be equal to 0. J is less than I, j plus plus, and yeah, you do something in there. Is there a problem still? Okay, let me drop these things before they will come and kill me. Okay, yeah, for something like this, we would call it quadratic, you know, because this loop is O of n, but inside that O of n, there is another O of n. So it's like for every single one inside that O of n, there is an O of n. So O of n squared. Okay, so before, there's also supposed to be log time. You know, there's O of log n and O of n log n, something like that. But we'll go into this place to try and read up on these two. In any case, let me explain why this one, where is that one? This one is called O of 1 and not O of 3. So there are some rules of thumb regarding what's it called? Regarding the big O. So one of them is that constants don't matter. So for example, let's say you did your counting, counting the operations properly, and you got O of 3n, right? The point of the big O, the O of something, is just to show the level or the kind of increase, or the kind of increase in operations that you would get looking at the big picture if you were to increase the sample size that you passed into that function. So 3n is just saying that, how do I put it? Whenever you increase the sample size, the number of operations would increase, based on that number of samples. It's not like a a squared increase like this one. It's still, you can still look at it like it's a linear increase. So this means maybe if it was 1, if n is 1, you'd have 3 operations. If n is 3, you have 9. If n is 100, you have 300. If you were to plot that on a graph, you still get something linear, a straight line going like this. So for that reason, constants don't matter. This would still be looked at as O of n. Also, small terms don't matter. So just like that one that we saw, that was 5n plus 1. For starters, we already said that constants don't matter. So that n, the 5 there has already gone away. Now this 1 is negligible, when put next to the 5, when put next to the n. Of course, if it was a small sample size, you might feel it's not negligible. But again, when looking at this big O, it's always looked at with the big picture in mind, passing a large number of items or data into the function. So take for example, n is 1 million. What does 1 count for? Next to 1 million, it's like nothing. So n, linear something. In the same way, if you were to have maybe count operations and you get something like n squared plus 2n plus 7, yeah, this is just n squared, because this 2n plus 7, once again, is very small in the grand scheme of things compared to the n squared. So one thing, constants don't matter, and 2, small terms don't matter. So we always go for the bigger term and remove the constants. Okay, so now let's go look at logarithms. I think it was here they tried to explain it. Okay, no, it wasn't here. So anyhow, let's just look at it from the beginning, shall. So as an instructor of front-end engineering, I'm often faced with a question from junior developers when it comes to talking about big O notation. Yeah, can't you get along as an engineer without knowing this? I think somebody even asked this, especially as a front-end engineer. So yeah, sure, there's no stopping anyone from brute forcing their way to a solution. But if you can remember, yesterday they talked about some guys, right, from Google. You know, they said how they mentioned, I mean, I'm talking about the group chats now. They talked about, you know, how in Google you make a pull request and it can stay for up to 4 months because everyone is just reviewing your code and throwing comments at you. But there's like 1 or 2 people that nobody talks to them. They drop their code and it just passes like that. This is because those people have made wonderful contributions to the company, and they've shown a very in-depth, you know, understanding of both the company's code base and, well, JavaScript as a whole. And part of their contributions was reducing search time, you know, in Google. So I don't know if they are back-end engineers or what, but you get the point. Even as a front-end engineer, the way you handle data can make a difference. If you had, you know, you are fetching a lot of data from the API, the way you handle it, do your calculations and all that, can be, you know, can make things happen maybe 5 seconds faster, or some time slower, that kind of thing. So while making it work is truly the most important thing, well, is best to make it work as best as you can. So here they talk about, you know, increased or a very large sample size. When it comes to scalability, these things matter. Just writing code now as someone who is just practicing, it's all good and all, but you eventually plan to either set up your own place or work for a big company. And with big companies, they are very, you know, clear on this scalability of a thing. They want a product that would perform well with small and perform well with big. And performing well, we've seen the 3 things that, you know, come to mind: speeds, memory, and readability. Well, that's for code, but the speed part works for whether it's code or whether it's implementation. So the fact is you can write code that works without knowing the ins and outs of big O notation, but it's difficult to tell whether big O is something you should even be considering when you are creating an algorithm if you have no idea what it is. In my opinion, dismissing foundational computer science fundamentals can help you make decisions and write better code. That can help you make decisions and write better code is foolish at best and disastrous at worst. So just saying now, after today's class, maybe from tomorrow, there are certain methods, there are certain, you know, they call it like types of algorithms that we'll be looking at that help to, you know, reduce the big O notation of your code. So maybe some certain reason or certain situations that would have made you want to write a nested for loop, for example. You can probably use one of those methods to work your way around it, that kind of thing. So after the point of talking about big O is so you see the importance of those algorithms that we're going to talk about later, and also the data structures as well. Okay, so what is big O? Big O is just the language we use for talking about how long an algorithm takes to run, time complexity, or how much memory is used by an algorithm, space complexity. So big O can express the best, worst, and average case running of an algorithm. For our purposes, we are going to focus primarily on big O as it relates to time complexity. So looking at it now, as we have this we look at a code and say this code is linear time or quadratic time. It serves as a way to generalize things. Like maybe if you were talking of earthquakes now, you could say maybe this earthquake is 7.4 on the Richter scale, right? And maybe this other one, sorry, what's this thing now? This other one was just a mild something. It was just 2.5. So you notice whenever they are saying the news and you hear these numbers, your mind already kind of generates some kind of image of how disastrous that earthquake is just by hearing the numbers, that kind of thing. So it's something like that we're going for with this big O. When you see a code and they tell you this is constant time, you say yeah, I mean this is the best it could be. It can't be any better than this, that kind of thing. So as a software engineer, you'll find that most discussions of big O focus on the upper bound runtime of an algorithm. True, you rarely hear of space complexity. Actually, at first I didn't know this was a thing. When I heard someone say this, I thought they were cracking a joke because time and space, that kind of thing. Okay. An important thing to note is that the running time when using big O notation does not directly equate to time as we know it, like seconds, milliseconds, whatever. Analysis of running time does not take certain things into account. Yeah. Such as processor, the language, or the runtime environment. Okay. So this is also part of what I mentioned earlier. Just looking at the time it took a certain operation or rather a function to run is not a very good measure, because like these guys have just said, whether it's the processor, the language you are using, or the runtime, I'm sure you've heard people say maybe this language is fast, maybe this one is a little slower, and all these kinds of things. Instead, we can think of time as the number of operations or steps it takes to complete a problem of size n. So that size n is an important thing there. In other words, big O notation is a way to track how quickly the runtime grows relative to the size of the inputs. So again, this just sounds like scalability. That thing that big companies always talk about, scalability. Whatever you write should, run well on small things and run well on big things. So big O just helps you track how efficient is your code really. How much more time would it take to perform with bigger sample sizes or data sizes. So when we're thinking about the worst case, the question becomes this: what are the most operations or steps that could happen for an input of size n? Okay, so O of 1, constant time. It means it takes a constant time to run an algorithm regardless of the size of the inputs. So best case scenario. Bookmarks are a great example of how constant time would play out in the real world. Bookmarks allow a reader to find the last page that you read in a quick, efficient manner. It doesn't matter if you're reading a book that has 30 pages or with 1,000 pages. The bookmark is already sticking out of the page. You just take the bookmark and flip, and you are back where you were. As long as you are using a bookmark, you will find that last page in a single step. So, in programming, lots of operations are constant, like math operations, accessing an array via the index, so like maybe array square brackets 5. Yeah, it's instant. It just gets you what you want immediately. Sorry. Accessing a hash via the key, pushing, popping, insertion and removal from a queue. Queue is a data structure. It's something we're going to look at later. There are data types, like strings, numbers, booleans, and the rest. There are data structures that we're going to look at. It's used for, or rather, they are used for, more efficiently working on certain things. There are things like queues, stacks, linked lists, double linked lists or doubly linked lists, trees, graphs. So returning a value from a function. Okay, take a look at find first index. Find first index listed below. Passing small collection or large collection or gigantic collection will produce the same runtime of O of 1 when accessing the 0 index. So this is small collection, this is gigantic collection. They just shorten stuff, but there's actually supposed to be a hell of a lot of stuff in between. So regardless of the size, okay, it's a picture. Regardless of the size of the input array, all the function does is return first index. Return the first thing here. So it doesn't matter whether you pass in a big array or a small array. It's just doing one thing. Okay, so now this is constant time. So next is linear time. It means the runtime increases at the same pace as the input. So the act of reading a book is an example of how linear time would play out in the real world. So you assume it takes 1 minute to read a single page of a large print book. Assuming all things being equal, a book that has 30 pages would take you 30 times 1 minute to read. Likewise, a book that has 1,000 pages will equal 1,000 times that 1 minute of reading time. Okay. Now I don't force myself. Okay, I don't force myself to finish books that aren't great. So there is always a chance I won't get through that 1,000-page book. However, before I start reading it, I know my worst case reading time is 1,000 minutes for that 1,000-page book. So in programming, most common linear time operations are array methods. Yeah, a lot of them are linear time. For each, you can already tell that this is a loop. This is a loop. This is a loop. So anyone that looks like loop already, you can tell this guy is going one time through the array. So the time is, or the number of operations that would happen with it, just are like the number of items in that array. Some other ones that we might not think of are things like index of, last index of, maybe search. Yeah, those are also loops that go through the array or go through the string to find something. So they are also linear time. Take a look at our print all values function below. The number of operations that it will take to look through n is directly related to the size of n. Generally speaking, but not always, seeing a loop is a good indicator that the particular chunk of code you're examining has a runtime of O of n. Yeah, mostly whenever you see O of n, it means there was a loop, or rather there's a loop somewhere in some form. Even if it's not a for loop, maybe it could be an array method like map. Okay, so print all values just goes through the array and prints, well, all the values, or rather, yeah, it prints console log. Okay, but what about the method find? Since it doesn't always run through the entire collection, is it actually linear? In the example below, the first value that is okay, I'm already here. Hey, say, don't worry. Okay, in the example below, the first value that is less than 3 is at an index 0 of the collection. Why wouldn't this be constant time? So, do you understand this question? Some, array methods, they don't actually, unlike map or for each that we are sure, maybe unless you put some kind of, in fact, map will still go through regardless. I don't know, I'm not sure for each, but most of them would are designed to go through the entire loop. But some, like search, find index, once they find what they are looking for, they stop there and come back. So it's not for sure that they will get to the end of the loop. They are actually more likely to stop somewhere in the middle of the loop. So they're asking, why wouldn't this be constant time? So remember, we are looking for the worst case scenario. Or rather, since we are looking for the worst case scenario, we must assume that the input will not be ideal. The input will not be the first item in the array. No, worst case scenario, the input or that thing we're looking for is at the back. It's the last thing in the array. So it's going through the entire loop. That's what we're assuming. That's the worst case scenario. So we're looking at that. Okay, so quadratic time means the calculation, runs in quadratic time, which is the squared size of the input data. So in programming, many of the more basic sorting algorithms, have a worst case runtime of O of n. You might have heard before, that they will tell you, as much as possible, avoid using array.sorts in your code, that it takes time. So later on in this DSA, we'll look at these sorting algorithms and understand why they are, O of n squared, and well, why they say they take time. So look at the operations, count operations below. We have two nested loops that are incrementing the operations variable after each operation. If n is our small collection, there are just 4 items, we end up with 16 operations. Yeah, that's not terrible. But what if our n is, gigantic collection with this is 1 2 3 1 2 3 1 2 3. I think that's a billion, right? This is 1,000 million billion. With a billion operation items. A billion times a billion is quintillion. It's a lot of operations. So even an array with as little as 1,000 elements would end up creating a million operations. So it's natural that these kinds of operations should be avoided as much as possible. Of course, if you can't help it, you can't help it. But if you can help it, do try to help it. Okay, generally speaking, but not always, seeing 2 nested loops is typically a good indicator that a piece of code you're looking at has a runtime of O of n squared. Likewise, 3 nested loops would be this disastrous thing you see here. So now, O of log n, logarithmic time, which is why we came here. O of log n means the running time grows in proportion to the logarithm of the input size. This means that the runtime barely increases as you exponentially increase the inputs. Finding a word in a physical dictionary by halving my sample size is an excellent example of how logarithmic time works in the real world. Yeah, this is good. For instance, when looking at the word senior, I could open the dictionary precisely at the middle, at which point I could determine whether the word that begins with S comes before or after the words I'm currently viewing. Once I determine that S is in the second half, I can dismiss all the pages of the first half. So it's kind of like a loop, but you are throwing away a lot. I don't know if you guys, I think this dictionary example is pretty good. A normal loop would have started from the beginning of the dictionary, check through A, B, C, D, all the words, and get to S. Then start looking at SA, SB, SC until get to SE, then SEA. That's it. But with this, well, as a rational human being looking through a dictionary, you wouldn't do that. You would just open somewhere and check, am I before S or after S? If you are before S, you go back to maybe another half point, like that, until you finally get to where you are going. So that's kind of, there is no, okay, so the main thing they said here is the runtime barely increases as you exponentially increase the input. Let's see if we can create something that shows that. So let's say we have an array. Let norms be equal to 1 2 3 4 5 6 7 8 9 10. Imagine we are looking for, imagine we write a function like yeah, this will take an array and a number n. Okay, so now the assumption for the arrays that we're going to pass into this function, the assumption is that the numbers inside it are sorted from smallest to biggest. Okay, so now our function is just going to generate an index. Let's call it half index. Right? So it's just going to be maybe math.floor array.length divide by 2. Okay, so if there are 10 things in here, 10 over 2 is 5. Our index is going to be 5. If there is one thing in here, it's going to be half over 2, that's 0. So we're all good, right? So it's just basically going to find some kind of midway point into the array, select that, and then it will now check if what's it called, if array square bracket half index is less, here, if the item at that index, that half index, is less than n, right, then what do? If it's less than n, that means the n we're looking for is bigger than the number at that half point, right? So we are throwing away the previous half. So I think this is like this is the kind of situation where you call it recursion. I don't want to waste too much time writing this function, so I think I'll just stop here. But how do I put it now? Maybe let's just manually go through it. Let's say we're looking for 7. The halfway point is 5, right? So if we check, we get 5, we throw away all of this and come here and check again. Halfway point should be 8. We pick 8, it's big. Maybe we throw away all of this. We're left with this 2. The halfway point will be here. We throw away this, and this is all that is left. We found 7. How many steps did that take? I think about 4 steps, right? Throw away, throw away, throw away, throw away. 4 steps. If we increase this to 20, 11, 12, 13, 14, 15, what? 16, 17, 18, 19, and 20. Okay, I wrote 1. Okay, 11, 12, 13, 14, 15, 16, 17, 18, 19. Okay, so again, let's look for 7. We've increased the size. So maybe midway point should be 10. Alright, 10 is bigger. We throw away all of this. Come to 5. Smaller. Throw away 8. Throw away 6. Throw away 7. So this was 5 operations, right? So you see, we doubled our n. The increase wasn't a double in the number of operations. It was just an increase of 1. So that was what they are talking about when they say the runtime barely increases as you exponentially increase the input. Even if we increase that input to 100 or 1000, as long as it's a sorted array, you would not get that many operations to find 7 inside there. So that is logarithmic time. So in programming, this act of searching through a physical dictionary is an example of a binary search operation, the most typical example used when discussing logarithmic runtimes. So let's take a look at the modified version of our count operations function. Note that n is now a number. N could be an input, sorry, or the size of an input, the length of an array. So we've got count operations, and let operations be 0, let I be 1, and while I is less than n, I is equal to I times 2 operations plus plus. Okay, so return operations. So while I is less than n, we just keep on doubling it and going up, that kind of thing. So in the example above, we end up with 11 operations if n is 2000. If n is 4000, we end up with 12 operations. You see that you basically doubled n just to get an increase in 1, an increase of 1 in the number of operations. Yeah, so that's kind of how it is. So n notes n log n, which is often confused with O of n log n, which is often confused with O of log n, means that the running time of an algorithm is linearithmic, which is a combination of linear and logarithmic complexity. Studying algorithms that utilize a divide and conquer strategy are linearithmic. This is a type of algorithm that we're going to look at later, such as the following: merge sort and heap sort. So when looking at time complexity, O of n log n lands between O of n squared and O of n. So this is a graphical representation. The way to get this graph actually is to take a function. Let's say a function that you are sure is maybe O of n, something like that, something, just maybe a simple for loop. You keep on increasing the n and you check how long it takes to run. So this is time and this is number of, well, okay, not really time, this is operations. Because we don't really use time for this. This is operations, number of operations and number of elements, number of the data size you're working with. So you can see the best one is O of 1, constant time, and O of log n, because log n is not really up to n, as we just showed, with that binary search. You can see it was less than the number of so this okay, this is the highest I can go. Oh wow, that's horrible. Hey, I don't lose. Okay, this dark green is the constant time O of 1. The lighter green is O of log n. The yellow is O of n. This is I zoomed too much. Okay, this is n log n, then n squared, well, 2 raised to the power n, well, n factorial. This is just horrible. Anyway, anything above n log n actually is in the horrible zone. You can see the color rating, kind of. So as much as possible, well, excellent is really hard to get in most cases. That's why it's hard to get this one. Most of the times you'll find yourself somewhere around here. Anyway, as long as you are aware that this is where you are, you see that you can't make it any better, no wahala. So one of my favorite sites to reference for Big O is the Big O cheat sheet. Blah 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 blah. As you can see from the charts, other runtimes have pretty horrible time complexity, like 2 raised to the power n and n factorial. Algorithms that run this don't fare well with anything but tiny data sets. 2 raised to the power n or exponential time doubles in time with each addition to the inputs. That's just terrible. And O of n factorial or factorial time is even worse. Anytime n increases by 1, the running time increases by a factor of n. Okay, so thus far we've only talked about calculating, we've only focused on talking about Big O by isolating a few lines of code at a time. So how do we calculate Big O if we're dealing with an algorithm that has several parts? So like I mentioned before, those rules of thumb: first of all, drop the constants. And maybe you get, you count all the operations and you get 2n or 3n or maybe 5n squared, drop the constant, just pick the n or the n squared. Yeah, or if you got maybe 20 operations, like constant 20 operations, yeah, the 20 is a constant, so it's O of 1 actually, constant time. And did they also talk about dropping the small drop the non-dominant terms? That's it. So I called it ignore the small terms. So if you have n square in there, something like n square plus n, this guy is small in the grand picture of things compared to this guy. It might look the same, maybe if you are looking at two things, this would be 4 and this would be 2, but turn this thing to 1,000, this becomes 1,000,000 while this is 1,000. What's 1,000 to 1,000,000? It's like nothing. So because of that, we ignore the small guy, ignore the little guy. So space complexity is not really mentioned so that much, but just that one is simple. It's just about the number of variables you have in your code, the number of what you use to store data in your variable in your functions. So the less storing of data you have, the better space complexity. So that one was just, I don't know, try not to unnecessarily create variables. If you can do without creating a variable, then do without it. Of course, sometimes you may not have a choice, like maybe you have an array, they are telling you to change the array, to do some things to the array, but don't change the original array. But meanwhile, in there you would have to do things like splice or, I don't know, push or pop, those kinds of things. Yeah, you have to create a variable to duplicate the array, that kind of thing. So as mentioned earlier, you can write code without understanding the ins and outs of big O, but be aware it's an approximation. As the runtime you calculate by hand may not play out when running in production, when performance is affected by things like environments, processors, languages. Anyway, this shouldn't stop you from learning big O. Having a good understanding of big O notation gives you more context about what does and does not matter when designing algorithms. Who wouldn't want that? So as we move on, I'd like us to look at big O notation of object methods and array methods, and why you should choose objects or arrays to store data in your functions at different times. Okay, the efficiency of the program, they just started like that. Okay, the efficiency of the program will be directly relying on time complexity. When we deal with a huge amount of data to perform operations like searching, sorting, access, insertion, and removal of an element, we could selectively use objects and arrays based on the need to enhance the performance. We can take the help of big O notation to compare and contrast the runtime for arrays and objects to understand them clearly. So let's understand the concepts. Okay, we've done all this. We've done all these. Okay, there we are. Now let's understand how objects and arrays work through the lens of big O. So objects will be used when we need fast access, insertion, and removal of an element, as objects are comparatively much faster than the arrays in case of insertion and removal. So I don't think I really need to talk much on that, but in any case, let's say we have an object. Let's sample obj with this. We've created an object. So we talk of insertion. Insertion is just sample obj dot my key is equal to something, maybe give, and that's it. You've inserted something. It's one way. Removal is just, yeah, I hope you guys know you can delete object properties. Delete sample obj, or should I just say dot my key. So after here, if you put a console log sample obj, you get this my key give. But if you copy this, come here and paste it, you get nothing. So both times one operation. Okay, so what else did it talk about? Okay, let's talk of access, have we? They said access, insertion and removal. Yeah, so with objects as well, sample obj dot my key, it does not matter how many keys, how many properties are in this object, you just have to do this dot the key and you get the value. So that's if you ask me, or I don't, in fact whether you don't ask me, this is one advantage that objects have over arrays. The fact that you just need to know the property name and you can just use that to easily access and very quickly get the value you're looking for. In an array, if you are not sure of the index of what you're looking for, you would have to run find or search. Is there search in arrays? I'm not sure. Anyhow, find. I know there's find. You would have to run find, and that's, you know, it's a potential O of n, because potentially worst case scenario you are looping through the entire array. So that's one thing there. So big O of objects: insertion, constant time; removal, constant time; access, constant time; searching is O of n. Searching in this case is, you know, like running a for loop, maybe something like you don't know the key but you know the value, so you'd probably let me comment these two out. I deleted them. It's something like, you know, for let's maybe key of sample obj. If sample obj key is equal to, maybe, I don't know, give, right? Then console log sample obj key, or perhaps do some other thing, I don't know. You could maybe choose to do whatever you want with it here. But yeah, this, oh sorry, in, my bad. Yeah, thank you. So for in, for objects, in case you are not sure, you know, what key holds this value, that kind of thing. So now this is just the only one that is O of n, because you are potentially searching or going to search through the entire object, or rather going to loop through the entire object. So that's why searching is O of n. But if you know the key, that's just regarded as access, it's constant time. So object methods, object.keys. This basically will just create an empty array, loop through the object and just put all the keys inside the array. So looping through linear time. Object.values is like the same thing, just for the values. Dot entries, it's like the same thing, but, you know, combines them. It has own property, you know, to check if a property exists in an object. Linear time, it's like access. It's just probably, you know, just check, does this thing exist, yes or no. Okay, so arrays will be used where arrays will be used where you don't need quick removal, sorry, quick access of things, because in arrays you can't keep track of all the indexes. You just know that this is an array, it has things inside, but you don't know what those indexes are. You have to search for them or use your eyes and look through it, which is just okay. So you don't need quick removal of things. You have a lot of things you want to store. You don't really have property names for those values. They are just values. Maybe this is the first value, this is the second value, that kind of thing. You use arrays. Insertion and removal are not as simple as with objects. I know pop and shift, they are all great, but here's the thing with them. This is what they say, it depends. It can be 0 of 1, it can be 0 of n, and this is why. Let's say you have an array. Let's sample array. Oh yeah, we had an array before. Yeah, this norms. Let me see if I can use that to explain this. Okay, so now let me now reduce this array a bit. Okay, so the index of this is 0, the index of this is 1, the index of this is 2, the index is 3, this one is 4. If you were to remove 1, you say, what's that? Is shift, Abby is on shift. Those things confuse me. I think it's on shift. On shift feels like it's on shift. Yeah,
Shift.
a shift. Okay. So if you shift, you've removed something from the beginning. Basically, you have changed all these indexes. 2 previously had the index of 1. So what that means is that you are now re-indexing all the things inside the array, right? So once you remove something from the beginning, there will be operations fired as many as the items in the array to just start basically looping over the array to give them new indexes. Okay, so now if you add something, okay, yeah, this is it's even annoying for me to do it by hand. This is now 0, 1, 2, 3. I shouldn't have deleted that first 0. Okay, but now adding something at the back, this will be 6. So adding something at the back is just one operation. All you are doing is just giving this new value an index of 4, that kind of thing. So the removal, okay, I have not even yeah, insertion. If the insertion is at the end, then it's O of 1, because you are just putting 7. It's just one operation, you give it 5. Naturally, if the insertion is at the beginning, you don't cause wahala with that. O of n, it would push everything and start giving them new indexes. If it's at the middle, it will now be like that kind log n. Well, not really log n. We'll still call it O of n, but you get the point. This is why insertion and removal in array usually carries these words. It depends. Access now here is the index. So like array index 4, that's access. It's constant time. Searching, just like before, just like with the objects, you don't know the index. For arrays, index is like the key. Okay. So you don't know the index, but you're just looking for that value. So you use something like find or a loop to go. That's O of n. So for array methods, push, pop, O of 1. Yes, O of 1, because you're just adding something at the back. Shift, on shift, concat, slice, splice, these are O of n, because um, depending on what you are slicing, you are giving new indexes to the new array you are creating, that kind of thing. Concat, you are creating a new array, new indexes. Shift on shift, we just talked about that. Whether you put something at the beginning or you are removing something from the beginning, you are causing a whole string of reindexing going on to the end. So O of n. These ones we don't even need to talk about why they are O of n. They are loops as you just see them like this. For each map, filter, reduce, find index. There are lots more. Just most of them are O of n. So actually, the message here is be careful how you use array methods, because maybe because of how simple they look, straightforward, you feel okay, it's nicer to write this than to write a for loop or to do things manually, if I put that in quotes. This carries, or this is expensive in a way. In programming, expensive is usually about time or space, something like that. So let's understand it with a simple example. Write a function that accepts two arrays and returns true if every value in the array has its corresponding value squared in the second array. Okay, the frequency of values must be the same. So if you have 1, 2, 3, there should be a 1, a 4, and a 9 in the result, in the second array, for this to return true. Okay, if this were to be 1, 1, 3, then we would expect a 1, and a 9. So just seeing 1, 1 would not be enough in that situation. So below is the array-based approach. Okay, this is let me just copy this. Okay, so there's the base case. If array1.length is not the same as array2.length, there's no point even bothering to check, because remember, the frequencies of the squared numbers must be the same. So if somehow there's a mismatch in their numbers, already is false. Then we just loop through the array. For I is equal to 0, I less than array1.length. They are both the same length, so picking any of them is alright. I plus plus. Let's correct index be equal to array2.index of array1 square bracket I squared. So basically, correct index is just finding the index of this. Like if you're looping over 1 currently, it would square 1 and find the index of that square in array2. So if there is no correct index, you get -1, because that's what index of does. It will return false, because that thing is not here. If it exists, then splice, it will cut it out, and the loop would continue. So basically, it will just keep cutting. If everything is the same, like 1 here, it will find 1, cut out 1. For 2, it will find 4, cut out 4. For 3, it will find 9, cut out 9. So once it has successfully gone through this array and no issues, then it returns true. So we understand this, Abi. So what do you think the O of the big O notation of this function is? Anybody? Sorry, I totally did not hear that. O of n. Is it O of n he said? Do you guys agree with that?
Thinking of n cube.
Cubed.
Yes.
Okay. So we have O of n and O of n cubed. Anyone else with a different idea? Maybe O of n quad? Any differing idea?
View is O of n squared.
O of n squared. Okay, so you guys now that are saying different things. Why are you saying the different things you are saying? Why do you say it's O of n squared? Let's go back and look at the function. This one is just, regular something like O of 1, right? It doesn't matter how many things are in these two. This one is just one check and that's it. This for loop is O of n, right? Let's push this out. Okay. Now look at this thing. What big O notation would this method have?
O of n.
O of n. What did I do? O of n. Now you have to remember that this is happening inside this for loop. So these two are, kind of like joined together. So this becomes O of n squared because you have an O of n inside an O of n. This one is just, okay, that's true. Splice. That's interesting. This is another O of n. Okay, so this is why you said you said O of n cubed. Okay. Actually, these two are like on the same level, so it's like O of n plus O of n. So it's like, 2n n. So at the end of the day, it's still going to be n squared because you have this loop and then you have maybe two separate loops running inside of it. Yeah, so it won't be cubed, it will just be squared. So yes, this is O of n squared because this is a potential loop, potential complete loop inside a definitely complete loop. Yeah, O of n squared. But this could be better. Sure, this works, and for small, data sizes like just 3 things or so, you wouldn't really find much difference. But we could make it better. One of the will I say popular algorithm methods that we are supposed to look at, or we are going to look at, is called the frequency counter. The frequency counter is just storing items in an array or from an array into an object. The reason why we choose objects is because of this stuff we talked about here. Objects have, easy removal, easy insertion, easy access. See, constant time for all these things. And we would not really need to do, or we would rarely need to do, even if we did need to do searching, it's not, like all the time, that kind of thing. So let's look at how we can use the frequency counter method to reduce the big O notation of this. let me write it up here so that I'll just change this later. New frequency function. So it's going to take, as usual, array1, array2. So we just create an empty object. Let's, I don't know, should we call it counter, be equal to an empty object. And then we run one loop over array1. Okay, I think it's still necessary to have this. In fact, if you ask me, it should even be on top here, because if we're returning false, no point creating this one. Okay, so we run one loop. Let's or is there any need for this? No need. Just let's num of array1. Yeah, so each time we meet a number in array1, we just throw it into that object. We did something like this sometime when we were talking about sometime during reduce, I think, or there's a question like this in the exercises for reduce, in a way you're supposed to count fruits, or is it mangoes, something like that. And I remember there was something about fruits in that stuff. So you'd say, you know, if mango already exists in the object, then you increase the value of mango by 1. If it doesn't exist, you create that property in the object and give it the value 1, that kind of thing. So that's just what we're going to do here. So counter square brackets num is equal to counter square bracket num or 0 plus 1. Does this line confuse anybody? We've used things similar to this in the past, but just to be sure, is anybody confused by this line? Nobody. Okay, so this is done. I think let's just console log what goes on after this. Console log counter. Perhaps I should also throw in more numbers. Okay, so let me throw in more numbers here. Maybe 1, 2, 2. And this should be 1, 4, 4. Yes. So you can see the counter. 1 shows up 2 times. Plum plum. 2 shows up 3 times. 1, 2, 3. 3 shows up 1 time. So that's just what the counter does. So now you can already imagine what we're doing next. We're looping through the next array, and then every time we see a number, we just reduce the count here. If it gets to 0, throw it away entirely. And so if at the end this is an empty array, well, you know you are good to go, that kind of thing. Okay, so now another for loop. Let's num again of array2. So counter square bracket num is equal to counter square brackets. Okay, it's supposed to be in brackets. Minus 1. Okay, so how do I put it? If it meets 1 this time around, it will drop this count here to 1. It meets 4 to drop this to 2. Another 4, drop it to 1. Another 4, drop it to 0. So now the thing is, at the end, we want to, if it turns to 0, we want to knock it off. Okay, so you can just add an if if counter norm is equal to 0, then delete it. Or it's even unnecessary to do this. We just do if counter norm is less than 0. Yeah, sorry. Less than 0, then instead of deleting, we just return false immediately. Return false. So what it means is that in that case, there wouldn't be any need for this actually. Okay, no, actually there's a need for this. Don't mind me. Okay, so at the end of this for loop, you return true. If counter norm is less than 0. So why is it returning false? Console.log norm 4. 4442222. Less than 0. At this point it's 3, right? Becomes 2. This makes it 1, this makes it 0. So why is it 4? Why is 4 making it less than 0? Oh, yeah. Okay. I forgot that we're supposed to square it, so I kept using the same numbers here. So we could either square here as we're putting it into the, so that here would show 1, 4 and 9, or here we square root it. And so I think the squaring is better, so I would square here. Okay, so counter, let's just say let square be equal to norm 2. Okay, so if you can see, we could have chosen to do this thing, norm, squaring the norm here and doing it here again, but that's just inefficient. It's an operation you can do only once here and save yourself, or rather save your function that time. In such a situation, yeah, it's advised to save up on that time and just create a variable to store that operation, or to store the value gotten from that operation, and then use that wherever you need it. So once you need to do an operation more than once, if you can help it, create a variable to store that the value of that operation, so you can use it later. Square. Okay, and this goes away. The fact that we're not seeing these console logs means this was not encountered. But if we did something now like adding 9 here, it will show false because of the first one. So let's add a number here to complete things. It's still false. So here, this second 9 probably. Let me change this to 25. So it is 25 that threw a problem. Okay. So that's that. If we try to check the what's it called, the big O of this function, we'll see there are just 2 loops. One loop, one loop. So what would you call this big O? What big O would this be? Yeah, anybody?
What did you say?
For this operation, for this function, what would the big O notation of this function be for time complexity?
O of n.
O of n,
Yeah.
right. So there are 2 loops. It would have been O of 2n, but then we have our rules that say we should ignore, what's it called, coefficients? Was it what this was called? A constant, ignore constant values, so O of n. And you see that's a big leap away from O of n squared. So these frequency counter methods, try to use it whenever you find the chance. There are other ones too, sliding window, multiple pointer, divide and conquer. Probably tomorrow or some other time we'll look at them. So I think this is a fair place to stop today's lesson. Is the class recorded? Well,
Was the class recorded?
I didn't start from the very, very beginning, but then I didn't start too far from the beginning, so you wouldn't really miss much. But it's recorded, sure. So anyhow, that's it. Are there any questions? Okay, so we have like 11 minutes. Should we just go find a nice question and see how well we can optimize code?
I couldn't answer it.
You couldn't do
I
it?
didn't really understand. That was why I was asking the class was recorded.
Okay.
I couldn't relate.
You couldn't
That's why I
relate.
was asking if the class was recorded.
Yeah, take out. Okay, so much information. That's interesting. Okay, so I have 3 recorded classes I've still not uploaded. I'll try and make good on uploading them and sending you guys the links. So we shall see tomorrow. We'll continue again with DSA. We'll look at.
Hey, please, before you go, please, can you go back to that code, please?
Okay.
Sorry, I don't know my network. I don't know. Please, can you explain this code?
This one.
Yes, please.
Okay, as usual, we're checking again if the 2 lengths are the same. If they are not, there's no point comparing. After that, we create an empty object. Yeah, so the purpose of the empty object is that as we're looping through the first object, we are storing each value and the number of times it appears in this object. Because, we are expecting there to be squares of all these numbers. This second array should contain the squares of all these numbers with the frequencies as well. So that means if there are 2, or rather if there are 3 2s in here, we are expecting to see 3 4s, since 4 is the square of 2, that kind of thing. So we are storing the numbers in here and their frequencies in this counter. That's basically what the counter and this loop is doing. You can see in this loop, we will first of all create square of the number. The reason why we create square of the number is because we are going to use this counter again for the second array. So if you square the numbers before you put them in here, then you just smoothly be checking the numbers later on when you are looping through this one. So square the number and then you use that as the key. So counter, square brackets, that squared number. I should have called this squared number actually. If counter square bracket square exists, you just add 1 to it. If it doesn't exist, you initialize it at 0 and add 1 to it, that kind of thing. So there was a console log here before. Let me add it back. So you can see 1 as a key 2 times, 4 3 times, 9 1 time, 16 1 time. So you can see these are squares of these numbers here. 1 is 1, for 2 that's 4, for 3 that's 9, for this 4 that's 16. So now we'll just look through the second array, and if we see any number like 1, now you see 1, you reduce the number of the value attached to it by 1. Okay, and so anytime you do that reduction, if you encounter a number that is negative, like for this 25 now, you see this now, counter square bracket num or 0. So since 25 doesn't exist in here, it will start out as 0 and subtract 1, so it becomes -1. So once you meet any number like that, -1, it means it did not exist in here. Or like, you get the point now. It means it didn't exist in this array, so you return false immediately, and that's it. But if you check through and no flags are raised, you check through the second array and there were no flags raised, then you return true at the end. So in this case, if I change this 25 now to 16, because it's this 4 that doesn't have its match here, if I change it to 16, you get true. So all understood?
Thank you so much. Thank you.
You're welcome. So while this one was looking all right, it looked like just you are doing only one loop, you feel yourself, because of this guy here and this guy here, you're actually not just doing one loop, you're doing loops inside a loop. So you should be wary of array methods, because not all are as nice as this. Well, they are important, there are sometimes you can't do without using them, but the thing is just take note that they are expensive.
Sorry, one more thing. Yes. I know that for the time complexity, I said it was 0 of n raised to power 2. Someone said 0 of n with n cube. I don't know what the answer was before I got through now.
Okay, so before I answer that, the pronunciation is O of n, or O of n squared, or O of n cubed, so that you not say it somewhere and they'll look at you one time.
Okay.
Yeah, thanks. So the answer was O of n squared. I know you see 3 O of n's, and I think that's why the person said O of n cubed. But the fact is that this for loop is O of n. But this loop and, well, not really loop, this method, this O of n method and this O of n method are inside this loop. It's just basically a loop inside a loop kind of thing. So it's just O of n squared. This is the basics. This is like what is going on here is just like for something for something you get the point. It's not 4 inside 4 inside 4. It's just 2 separate 4s inside one 4. So it's O of n squared. I hope that makes sense.
Yes, it does. So at what point would you have O of n cube?
When it becomes like this.
Another loop outside again.
So when it becomes a 4 inside a 4 inside a 4, that's when it becomes cubed.
That's like nested.
Triple nested for loops. But just this, for example, this one like this now, this is just O of n because there's no 4 inside. It's like this is O of n plus O of n, so it's like O of 2n. But then, we look at the big picture. We say we should remove, or rather ignore, constant values. So if you see, where did I write those? Yeah, if you see O of 3n, you would actually call it O of n. Alright, so that's that. Any other questions? Nothing. Okay, I hope you guys had fun. We'll see ourselves again tomorrow.
I wish I did.
You didn't come early now.
I did, honestly. Thank you.
If it is not this early like Sinko, I don't know, send me work.
Okay, you guys had something today. Hard luck. Alright now, so later tomorrow.
Thank you.
Bye. Thank you.
Welcome.